Here's another lecture video for the lecture Intro PDE. In this lecture we present section 4.5. In this section we introduce the heat kernel. This is the analogous function for the heat equation, which is analogous to the Green's function for the Laplace equation. So we have an open domain omega in Rn, and then the heat kernel is characterized by two properties. First, for given x and t in omega cos r plus, the function y going over to heat function evaluated at xyt extends continuously to the closure of omega and vanishes on the boundary. Second property, for any x in omega, the function y and t, which maps to heat function evaluated xyt minus fundamental solution evaluated x minus y comma t, solves homogeneous heat equation and extends continuously to the closure of omega times non-negative numbers t with value 0 on the slice corresponding to t equals 0. Okay, now there's first a lemma which is analogous to Green's representation theory. Okay, now the proof is quite simple. Also, if we look at this, all the terms where we have t derivatives, so this product here and this product, this product and this product, then it's by the Leibniz rule, it's just an integral over the t derivative of this times this function here. And so by the fundamental theorem of calculus, we can we obtain for this integral this difference here, evaluated at t, small t equals capital T minus evaluate small t equals 0. Okay, so this gives this integral, and this terms here, this product here, and this product, we make a partial integration. So this is the divergence. So we consider this as the divergence of the gradient of u times gradient of v minus gradient of u times v. And the remaining terms, by the second lemma of Green's second lemma, the mixed terms cancel, and so we only get boundary terms. So we only get the boundary terms, and the boundary terms we have written here by the divergence theory. So this just follows from two partial integrations. This is more or less straightforward. Now we apply this. For this function. We insert for v the heat kernel. Okay, then clearly we get more or less problems, since at 0 this is not well defined. So this term, for this term we have a problem, and in order to avoid this problem, we instead of integrating from 0 to capital T, we integrate from 0 to t minus epsilon, and then take the limit epsilon going to 0. Then we get here Vx epsilon and times Ux capital T minus epsilon, and we get here Ux epsilon no, this term is the same. Yeah. Okay, and in the limit epsilon goes to 0, yeah, by the second property, yeah, by this property, and by the theorem 4.3, yeah, which gives us the solution of the initial value problem. The convolution with the fundamental solution gives a solution of the initial value problem. So we see that in this limit, this term here just gives u of xt. Yeah, this just gives u, this integral here gives u of xt. If we insert this, and then clearly, since V solves homogeneous heat equation, this term here vanishes, and this term here we have written here. And the first integral vanishes, and the second integral we have written here, and then we have this boundary terms. Okay, this is just this boundary term. This here is this this boundary term here. This term here vanishes, since heat function vanishes on the boundary, yeah, by the first property, yeah, this term vanishes. Yeah, so this term vanishes and this term vanishes. So we get this term, which is this integral, and on the right hand side we have this term, and then this integral gives this term, yeah, by this limit, yeah, and then epsilon going to 0, and by theorem 4.3, and this integral finally gives this integral. Now, if we bring this to the other side and bring all other terms to one side, then we have this term is equal to this integral here, and then minus this integral here. Plus this integral, if we bring it to the other side, plus this integral, which is just here this integral. Oh, here's an omega missing, and then this integral is this integral. Okay, so now we have this formula, and this formula is very nice because it tells us, remember that we look for the following problem. Yeah, we want that u dot minus Laplacian u is equal to f on omega cross r plus. Yeah, we want that u restricted to d omega cross r plus is equal to g, and u restricted to omega bar cross 0, this is equal to h. Yeah, so this is our initial and boundary value problem. Initial and boundary value problem. Yeah, for the inhomogeneous heat equation. And this is what we want to solve. Yeah, and this problem we want to solve with the help of the heat kernel. And if you look here, then all these three integrals, they all correspond to one of these conditions. Here we have this term, yeah, so we should replace this by f. Here we have at the boundary, so we should replace here u by g. And here we have the initial value, so we should replace here u by h. And so it's very natural, yeah, to write here f, to write here g, and to write here h, and then hope that this gives the solution. So this is the content of the theory. So let f be a function, and g a function, and h a function. So f is of course a function here on this domain, yeah? Or maybe if we restrict, then we say 0 to t. And maybe here open parabolic cylinder. Here again we have d omega cross 0 t. And here we have this. Okay, so we have this function here, this function, and h a function on omega or omega bar, extending with appropriate regularities, as we will specify this later, such that all appearing integrals converge absolutely, and then the claim is then that in this case we really have that this solves the unique solution of the initial boundary value problem. Yeah? Initial and boundary value problem, which I described here. So this is exactly this problem. Okay, here this theorem, one needs also to be more specific. Yeah, one needs of course to consider special domains. Yeah, because the concrete conditions, they depend on the properties of the heat kernel, and this depends on the domain, especially on the behavior of the boundary. How much regularity has the boundary of omega? Yeah. So now we want to first prepare the proof, or the sketch of the proof of this theorem, by again showing some symmetry of the heat kernel, yeah, as it's completely analogous to the Green function, where we also showed some symmetry. Yeah, so we have for all t larger than 0 the following symmetry. So if we replace the two arguments of the heat kernel, then the heat kernel doesn't change. So how we do this? We insert on one side for u the heat kernel with xz, and for the other the heat kernel for yz. Yeah? This proof is again very similar to the proof for the symmetry of the Green's functions. And then we insert this in lemma, and then, okay, in this lemma here. So we insert this in this lemma. Then clearly this term here is the heat equation for V, so this vanishes. This is the heat equation for U, so this vanishes. So here we have U evaluate U on the boundary, so this vanishes. Here we evaluate V on the boundary, so this term vanishes. So we get all together that this is 0. Yeah, this two integrals are 0, but these integrals are again by the same argument as we had here. Yeah, so we should take limits. We should take integral from epsilon to t minus epsilon, and then take the limit epsilon going to 0. Then this will, yeah, because V is a heat kernel, has a singularity at 0. So this is not well defined, but in the limit we just get the value of this function. So we get u of x set t. Yeah, by we get at so we get so we insert this, and then by taking the integral, we get the singularity is at y, so we get x. We should, in the first integral here, we get x y t, and here for the heat function u, we have the singularity at z equals to x. So this means here we have to set z equals to x. So then we get exactly this difference, which is 0. So we get really the symmetry of the heat functions. Yeah. Also, to make it more clear here. So if we insert here the heat kernel evaluated at x set, so for this set here, which we integrate, has a singularity at the x. Yeah. Sorry, here in this term. Yeah. So this has a singularity at x. So we should set here the set equal to sorry, this has v is the heat kernel at y set. So this has a singularity if x is equal to y. So we should set this x to y. So we get this heat kernel. And here, this has a singularity if the x, which we then call set, is equal to y. No, sorry, to x here. Okay, and in this way, we get these two expressions which vanish, and so the difference vanishes, so they are equal, and we have shown the symmetry. Now let's see how the sketch of the proof of this theorem works. We have these three terms here. Yeah, here we have this term, and this term, and all terms. This term corresponds to F, this terms to G, and this terms to H. Now first we consider that F and G are equal. Then we only this term remains. But by the second property of the heat kernel, by the second property we know, and by this theorem, we know that this then really gives the fundamental solution. If t goes to 0, then we get H. So we really solve the problem, and since this vanishes at the boundary, we have the correct boundary value, and since H solves homogeneous heat equation, it solves really the problem of the initial value problem. So this is easy. The case, so this case, A if equals 0 if G. This follows now just from the definitions of the heat kernel and our theorem in the beginning, where we solved the initial value problem on Rn. Now, let's look for the second case. The second case is G0 and H0. But then we look for this integral. First, in general, we have this integral. But we first look for this integral without integration over t. Then, by our first property, we know that this solves this initial value problem. It's 0. It solves the homogeneous heat equation, and it's it has this value, of course, at t now, and on the boundary it's 0. Now, if we assume that has appropriate regularity condition and extends twice continuously differentiable to this, then the integration, then we may apply the fundamental theorem of calculus, and then we see that this really, if we take here the derivative with respect to t, then we get one term here, which we already understood, and the other term we get here, which we might here, which we might transform to the heat equation, and so we know really that this solves this equation here, and it's 0. Initially it's 0. Yeah, why it's initially 0? Yeah, because for t equals 0, the integral, of course, this integral goes to 0 if t goes to 0. And since this already vanishes at the boundary, yeah, this also vanishes on the boundary. Yeah, here this follows from Duhamel's principle. Yeah, I should notice this. Yeah, this again, that this is true, this follows from Duhamel's principle. Yeah, it's the same method how we constructed the solution of the inhomogeneous equation by taking an integral over the solutions of the homogeneous initial value problems, where we inserted as initial values the inhomogeneity. Yeah, this is Duhamel's principle. By Duhamel's principle, we get this, and this just follows here by the integral and the regularity, and this follows by the properties of the Green's functions. Finally, yeah, so it remains to consider the last case, yeah, because of course we can separate. Also, if we have these three terms, we might write this as three sums. If this solves the problem with g equals 0 and h equals 0, if this solves the problem with f equals 0 and h equals 0, and if this solves the problem with f equals 0 and h equals 0, then the sum solves the complete problem. Okay, so in this sense we may prove this separately, and now we are in the last case. In the last case, only g is f is 0 and h is 0. Now we extend this function with appropriate regularity to this function. Yeah, and we do this such that it vanishes outside the tubular neighborhood. So if we draw here our picture, t, let's say here is 0, here is omega, and so we want this to vanish here in tubular neighborhoods of the boundary. Yeah, so this means we have a function here and extend it such that it goes to 0 twice continuously to 0, and then set it here 0. Yeah, in a tubular neighborhood we go to 0. Okay, so we extend our function g to a function u tilde, and now we subtract from u tilde the solution of first of this problem with this initial value and of the second problem with this inhomogeneity. Yeah, and then we clearly obtain a solution of the desired boundary value problem. Yeah, so in this is the sketch of the proof, how we might prove this for a domain if we know heat kernels. Of course, the appropriate regularity in all the statements depends on the heat kernel and therefore also on the domain. All the time, of course, we assume that the divergence theorem holds for the open domain. So now we have another important property, that the heat kernel is always positive on the parabolic cylinder if it exists. Yeah, this follows by the maximum principle. Okay, the fundamental solution is clearly positive, and then the difference of the fundamental solution minus the heat kernel is the unique solution of the heat equation, of the homogeneous heat equation, which vanishes on the slice at t equals 0 and coincides on the boundary. Here it coincides with the fundamental solution, and here it vanishes. So this solution is for all epsilon, of course, and on this not larger than this function here, since this is positive. And then by the maximum principle, it's smaller than this function, so this is positive. By the maximum principle, is the heat function now is smaller than the fundamental solution. Sorry, this difference is smaller. This difference is smaller than this. So this function is positive. Okay, what we have done, let's recall in this section. We introduced the heat kernel by two properties. Then we showed an analogous identity to Green's representation formula. This is also similar to Green's first and second formula. The consequences we used again more or less Green's second formula, and then we obtained this formula, and this suggests this solution of our initial and boundary value problem. And then we proved this, or at least we gave a sketch of the proof, but first we showed the symmetry of the Green's heat kernel, the symmetry of the heat kernel, and then we proved the theorem. Okay, I should emphasize that in this sketch we use this, where we use this symmetry, because, for example, here we need, if in this expression here, if f and g is 0, we need that that the heat kernel vanishes at x. Here this if x belongs to the boundary. But we had a problem that the heat kernel vanishes if y belongs to the boundary. So by the symmetry we get this. And similar here, we need this expression as a function on x and t solves heat equation. But we had that it as a function as y and t solves heat equation. So we at these two places we needed the symmetry. Okay, and then we proved by this we sketched to prove that for sufficient regularity, regular functions f, G and H. This really solves our boundary and initial value problem. And finally, we proved the positivity of the heat kernel. Thank you.